Welcome to lecture 7 of MCS 507, course on mathematical, statistical and scientific software. So this is the middle of the third week, and the third week has as topic arithmetic and interfacing. So today we won't really do much about interfacing, so the focus is entirely on arithmetic. We will be using multi-precision arithmetic as provided by the GMP library, but then we will see two other arithmetics, mainly interval arithmetic, and then at the very end multiple double arithmetic. So the interfacing is in this lecture done by either Python or Sage. On Friday, I will promise to say something more about the technical issues that, for example, would occur if you wanted to extend Python with a shared object encapsulated by then Python code. So last time we started this week with root finding, and root finding is actually a very important problem in which one can make good use of extended precision arithmetic and also in working with interval arithmetic. So we actually start a lot easier, or let's say with an easier problem, but actually a more important problem, because if you cannot evaluate an expression correctly, then the question of root finding is actually not so relevant anymore. So I took this expression from proceedings of the Scientific Python Conference, which is a motivating example for interval arithmetic. So then there is a survey paper published in Acta Numerica. So Acta Numerica publishes survey papers on numerical techniques, and here if this is your first view on interval arithmetic, then that could be a good source, although there are also textbooks that teach numerical analysis making good use of interval arithmetic. Interval arithmetic has the promise to compute rigorously, so you have control over your round of errors. The slides are set up from the perspective of running scripts. So there are a number of scripts that are posted at the website. There is also a Jupyter notebook with a Python kernel that runs things all at once, so to speak. So here is the expression defined in a Python session. We do this twice. So we start actually with, it's a numerical expression. The fact that it is numerical is implicitly, or is actually explicitly also defined by the .75 in the number 333. So even if we evaluate this at an exact number or at a pair of exact numbers, so this is an expression in x and y, then you see that it turns out to be a numerical value. Although here I must confess that I also, you can see that I say it's forced to be floating point arithmetic. So naturally, as soon as the numbers start to become 64-bit floats, then one can hope only to have an exact an approximate computation. So one evaluates numerically. One can say that's the end of it, but actually it's not the end of it. So let's verify. Here I did now the evaluation exactly, and you see that I had to redefine the expression. So the 333.75 is now defined with exact rational arithmetic. So the previous computation was forcing it into float, but it would already have been inaccurate if I left the 333.75 in there. So in order to make it proper, what I did, I made sure that the function, so the expression is no longer a function, it's an expression, a SymPy expression using explicit rational numbers. So I make sure that all divisions are done with exact arithmetic. So you can see what the exact value is. I then rounded this to floats. So the numerical value is still here, so this is the execution of one script. So the numerical value is way off. So the error is 2. Not good. Okay, this was in some sense quite a sobering calculation. When we use when we use floating point arithmetic, we have a precision of about 16 decimal places, and we can lose a couple of decimal places. But here actually the error, we have lost all precision. So none of the decimal places we computed was correct. Now, in a numerical analysis course, we could justify this, but let's do this now automatic. Let's say, well, you know what, the multi-precision was not enough. So I'm using the mpmath that I then installed as a standalone package. I will give the reference in a minute. So let's do this with 30 decimal places. So with 30 decimal places, I get 1.17. So the mpmath multi-precision allows me to set the number of decimal places to 30. So this is actually quite nice. So also my function now works within the setting of 30 decimal places. Now you see that all the constants, all the numerical constants, are actually converted into multi-precision floats of 30 decimal places. So in order to make the experiment work well, I also converted the numbers, the input numbers, coming from their string representation, converted them into multi-precision floats to make sure that mpmath will see them as multiple precision floats of 30 decimal places. So in the lambda function, I left the integers. But all the decimals were actually converted to 30 decimal places. Okay, so you see the 1.17, as we remember, is still there. So we needed actually a negative number. And then you see, if I try to play with this, 31, 32, 33, then 35, and then all of a sudden 36 has a dramatic change. So this indeed is a motivating example for interval arithmetic. Some people will say, well, just try a little bit more precision, and if the answer doesn't change except for the extra decimal places that you compute, then you are safe. No, you are actually not. So in a proper numerical analysis course, we would compute the condition number of the evaluation problem. So that would then be the reply of the more classically schooled numerical analysts. Well, estimate the condition numbers for this expression, and then you could justify, you could estimate how much precision you will need. But at the software level, as somebody who is not traditionally schooled in numerical analysis, then actually just changing the precision is not enough. So you would have doubled the precision from 16 to 32 and thought that everything was fine. Or from 15 to 30 and thought that everything was fine, but it is not. Okay, so let's do a detour. I was using mpmath, but actually if you are running things in the cloud, then SageMath is perfectly fine. Coming back to the root finding problem, I indicated how to give the fields, so looking for integer roots, looking for real and complex roots. You can also actually compute with rational arithmetic. So, but then kind of give the diameter of the enclosing intervals. So here you can see we can use interval arithmetic to isolate the real roots. So the algorithms are interesting, but I will bypass them. But you probably have heard of, so when in numerical analysis we did the bisection method to determine whether there is a root or not. So you by using the intermediate value theorem. So this actually can be generalized and make to general good use for exclusion-inclusion method. So bracketing roots is very efficient, is very effective for isolating all the real roots. So here you see the isolating intervals for the real roots 1, 2, 3, 4. So I get rational expressions. So in a way we are approximating the roots, but we are approximating with exact rational arithmetic. You see here the intervals that are enclosing the roots. Okay, this also actually applies to solving linear systems. So here is an example. If you have coefficients with very limited precision, so here I'm actually giving a matrix. I'm giving a matrix defining by intervals. So it's a 2 by 2 matrix. So I have over the real field, I have given intervals 2, 2, minus 1.11, minus 1, 1, and then 3.7 and 4. And then I ask for the inverse. And you see the inverse, it is actually still a regular matrix. You see but I have very, very little precision. So the question mark is actually indicating that for the number of decimal places, so the 2, 2 gets kind of inverted to 1/2. I have on the diagonal, I'm sure enough of numbers that are not 0 yet. So I can solve a linear system with this. And you see that the solution is kind of 1, 1. But there is kind of a large diameter. So in some sense, this is automatic error analysis. So with the interval arithmetic, I can determine bounds on the solutions of the linear systems. So this is very well wrapped into Sage. So the reason for going to Sage is actually you have your linear algebra extended also to the interval arithmetic, to various arithmetics. All right, I mentioned mpmath, so it's available if you install SymPy. You actually get it for free, I think. But you can also install it as a standalone library. It works quite well. So that's the main reference for mpmath. So one can use it to experiment in a standalone Python session with interval arithmetic. We define our interval arithmetic over the floating point numbers. So here the number of decimal places is 15. So in a way, with interval arithmetic, you can go all the way out, so like we did with the real roots in Sage, but here you're much more closer to the machine arithmetic. So we are working with intervals where the endpoints of the intervals are not rational numbers, but they are floats with 15 decimal places. So you see that we can divide. So the division works as long, of course, that the origin, that 0 is not a member of your interval. So we can divide one interval by another interval and obtain another interval. So in general, one has functions of intervals. So for any function that you define, for any continuous function, we have this property here for interval arithmetic. All the mathematical functions are predefined as well. So we have the logarithm, the sine function, the cosine function. Pi is, of course, we can work with pi. And here you see all the outcomes. So the diameter of the interval gives an upper bound, gives an estimate for the accuracy of the computations. So in some sense, if we did numerical analysis, we did not push it that far, but one can think of the promise of interval arithmetic, that you can do numerical calculations, but with some extra work, so there is some overhead here, you get a bound as well on your computations. So you get somehow an automated error analysis. And this leads to the promise of rigorous computing. More about instantiation. So this is a technical issue. If you work with if you turn a number into a multi-precision interval, that if you give the number itself, it's going to assume that you want to compute with that number. But if you give a string, you actually have already then an error of the string conversion. So here you see that you work with now an interval where the 0.1 has a representation error. Lecture number 2 of numerical analysis shows that 0.1 is a problem. 0.1 is 1 over 10. But 1 over 10 for us with 10 fingers is actually an exact number. But in binary, 1 over 10 does not have a finite expansion. So there is a representation error. So in some sense it looks like a technicality, whether you want to work with 0.1 and you actually see the representation error. So we see the 555, at the very end. So that's already something is wrong here. But with interval arithmetic, you capture this right. So the 555 at the end is kind of an overestimate for your bound. The left is then actually the lower estimate. So the true 1/10 lies somewhere in between. But don't worry, you still have 15 decimal places. But know that in numerical analysis, if you work with the floating point numbers, you have errors getting in there. Even if, say, you would be thinking that you work with the exact 1/10, you work with an approximation. Okay, there are attributes. So I showed the diameter of the interval, which was how it was called in Sage. Here we have the width, so there is the delta attribute, you have the middle of the attribute, of course the left bound and the right bound. There is an internal representation of any number. You can actually get the fraction and the exponent as well out of there. This goes perhaps a little bit too deep, but what the mpfr or the multi-precision arithmetic here does, so we set the number of decimal places to 15, it actually follows kind of how the IEEE does its floating point arithmetic. So you have a fraction that you can get out of there, you have an exponent. So it is software driven floating point arithmetic. Alright, so let's now cut back to our original problem. We had almost forgotten it. So this is the evaluation of an expression in two numbers. So remember, recall that we did the evaluation with an increasing number of decimal places, starting at 30, 31, 30, and then with 35, we were still not seeing any difference. But here you see, if you do interval arithmetic, at 35 decimal places you're still wrong. But the point is, you know that you are wrong. So I have done this multi-precision arithmetic with the definition of the expression where everything is evaluated with 35 decimal places. And I did the correct string representation with the instantiation with strings. Now I think that every constant, except 1 and -1, but all the numerical constants are actually now represented as intervals. And you see that the interval is very wide, so you cannot even be sure of the sign. So the sign is negative, but the interval is so wide that it also contains both negative and positive numbers. So this is an indication that you do not know how many decimal places, but now actually you do know as soon as you hit 36. So with the interval arithmetic, one does have a bound on the error. And we know that it's quite precise. So we have, we are losing here only 6 decimal places. So we have the exact value of the expression at these points A and B for x and values for A and B, the values for x and y, we have 30 decimal places. Okay, now comes a word of warning. So why not flip entirely to interval arithmetic and do always that. Now it's actually not so so trivial. So I will say something how one should not use interval arithmetic, and that in some sense spoils it, but also explains why it's not so much more widely used. So here we consider the naive application of interval arithmetic. We have an expression that we want to evaluate. So we want to compute the square root of 2. In numerical analysis, when we see this, we see that this is a quadratically converging method. But we also want to do so the x squared minus 2, so we are doing root finding on an expression x squared minus 2 that is of course very easy to evaluate. So we don't run into the trouble there. But fine, we still want to have somewhere an estimate of our round off that we do. So, okay, so the naive application of interval arithmetic will replace every instance of x with an interval. So that's easily coded up. So that's here the point. So I have now a capital X, an interval. So instantiated appropriately with these strings. So it's the naive application of the interval method. But here you see again, so the dubious reputation of interval arithmetic. So as soon as you use interval arithmetic, the main question is, in order to make it make sense, how wide are the intervals getting? And it can get extremely bad. The intervals can get wider and wider. So this is now a demotivating example of interval arithmetic. But why is this happening? Well, the problem is that we had one single variable, but we replaced this with different numbers. So the bounds in the interval are actually tied to each other. So the way in divisions things get wider and wider. And in some sense, we did this already earlier. I could have warned you when I showed the division there, is that especially when you use the same number x in the numerator and the denominator, you can actually get a lot more tighter bounds. So the division operation is executed assuming that the numerator and denominator are actually completely different numbers. So and in general they can, but if you see a division like this, you should actually not do it like that. So the x in the numerator is the same as the x in the denominator. Okay, so there is a principle there which I will apply here. So this is a principle that is used in inclusion and exclusion. So Newton's method is so important is that it refers to the contraction operator. So if the Newton's method is converging, then if you apply the Newton operator, then the Newton operator is now seen as one operator, an atomic operator almost, operating on these intervals a, b. So a, b applied symbolically, now x is still a symbol here, will actually give you an interval that is smaller. So the theorem is actually if the interval that you get from there is smaller, then you have a unique root. Okay, so then there is the second part in this theorem that says that if the intersection is empty, then actually that's the exclusion part. So you can use interval arithmetic very effectively in this way. So the inclusion part, so the first part of this algorithm, is a criterion for deciding whether to decide that you have an interval that contains a unique root. And that's done with the Newton operator, which is not the naive operator from the previous slide, but which will be the Newton operator from the next slide. So the second part in this theorem is the exclusion step. So this is the theorem that is most likely behind the earlier calculations that were shown with SageMath, where I showed an example how the roots 1, 2, 3, 4 were approximated by intervals of rational numbers. So the inclusion-exclusion theorem can be used for that. Okay, so when one does this, so we have actually a Newton's method that is contracting, and we replace in every step the interval by its midpoint. So that's the proper use, giving that in this operation we have the same x in the numerator and the denominator. So that then leads to nicely converging Newton's method with an extra upper bound. So we actually know, so if we run this in a numerical analysis, we could think that all the numbers that are displayed here are correct, because in the previous two steps we have the same bound. But note that in numerical analysis we say that this is an estimate for the forward error. It's an estimate. Interval arithmetic will actually tell you that you should not trust here the last 5 decimal places of what is displayed. So there are these error bounds. Okay, so I deliberately did not want to overload you with too much material. So I have one other arithmetic, which has the benefit of extending the precision, but still exploiting the floating point built-in arithmetic. So here is, in a nutshell, what it is. I learned through it via the QD library. So that's my first reference. So there is the double-double. So we have the double precision float. A double-double is like a complex number. So you have a first part and you have a second part. So you work with tuples. But it's actually an unevaluated sum. So we are representing a number as a most significant part and then a least significant part. And you can see this as the least significant part, which is again a double, and that's of the magnitude of the precision you're working with. So with double precision, you can double the precision, double the double precision, you get about 32 decimal places, correct? With quad-double precision, you quadruple the double precision. Well, what's the point? We can already do that. But the point is here is that we keep on working with double precision. So it has a very predictable overhead. So almost all modern computers are still optimized for double precision. arithmetic. So one has a very predictable cost overhead. So it's not software-driven arithmetic, but it's still hardware double precision arithmetic. Okay, here is a property. So this is the relationship with rigorous computing and the property of error-free transformation. I first learned from the survey paper that I mentioned in Acta Numerica. Here is a computation that we can do. So as a test, if you take random complex numbers where the numbers are randomly generated on the unit circle, you take 64 of them, and the 2 norm of these numbers, so you have a freedom. If you take them on the complex unit circle, you can choose the angle of all of them at random, independently. So, but no matter how independently you choose them, the 2 norm equals 8. Now, what happens when you do this in double-double arithmetic? The leading, so the point is that 8 can be represented exactly with floating point arithmetic, with 64-bit floating point arithmetic, and it's overkill to use 52 bits in the fraction part. But the second part in your double-double also gets quite small, so it is an indication of the precision. So the error-free transformation, the property, as I learned to appreciate it, is that if the number that you are computing can be represented exactly within the double precision, then your second double, and even if you compute with 8 doubles, your second double will show the precision. So we'll actually, in that sense, the precision here for this example, but precision here also equals accuracy. So we have computed the number 8 with 32, 64, or 128 decimal places. Okay, so there is double, quad double, but there is many double, and as many doubles as you like, if you are using the software provided by the CAMPARY library. And the first letter in CAMPARY stands for CUDA. So CUDA is the Compute Unified Device Architecture, the standard used by NVIDIA if you want to implement anything on graphics computers. So this library was targeted for extending the precision. It's also available on float. So not all graphics cards, or some graphics cards, are specific for floating point arithmetic, single float, not double float. So you can then do this library, use this library and implement the extended precision on the graphics processing devices. So this is where it gets closer to my research interests. So the graphics cards have teraflop precision. General processors work at gigaflop performance theoretically. So giga and tera, there is a magnitude of difference. And the motivation is to exploit the GPUs to get more precision. So in this course on software, we will use libraries that are available. I can give you access to GPUs if desired. If not, wait till the supercomputing class, where we talk more about GPU computing. Now, there is one important reference here. I did not say too much about floating point arithmetic. The last reference is available through our UIC library. And this will surely, this is a resource that contains more than you ever wanted to know about floating point arithmetic, including the multiple double arithmetic. So notice that there is an overlap between the software library CAMPARY authors and the writers of this handbook. Okay, to conclude with some exercises. So the exercises concern mainly interval arithmetic. So the way the expressions are written matters a lot. So here, try to explain with a graph what happens if you evaluate these two quadratics. So one form is better than the other. Try to understand why one is evaluated better than the other. In the second exercise, the outcome is actually terrible, and you can't really improve on the outcome because the origin, the 0, is included in X. The third interval, the third exercise is more open-ended. So in my experience, in my experiment, earlier on the slides, I actually took a matrix that was very well conditioned. So I could still invert it with providing very wide intervals. If you have a singular matrix, and you can make one that is very close to a singular matrix, the singular value decomposition is useful there, then you will see that your intervals will need to be quite small. So the purpose of this third exercise is here to make the relationship between the condition number of a matrix, how far you are from a singularity, and also what this interval inverse gives you. Okay, so the point also of this experiment, and perhaps we may extend this to a first computer project, is that if you are using properly coded libraries, software libraries, then actually the interval arithmetic is used appropriately, not naively as we did in one experiment with Newton's method. Okay, so the last exercise is kind of optional. It assumes that you are familiar with working with C and C++ code. So I may demonstrate this in the next lecture. So the QD library is actually quite easy to use. It's very self-contained and installs well. Now, of course, this, again, if you're unfamiliar with C and C++, then this is not the case. So that's why I leave the fourth exercise more as optional. Okay, I conclude here. So I hope this has given an overview of the arithmetic, which is more a hybrid. So interval arithmetic, you can do this still in a very exact manner. So interval arithmetic can make the bridge between exact computations and purely numerical computations, for which you need to understand numerical analysis. And the exact computations you may not. Then the numerical analysis is entirely optional. So there is a spectrum in between them, where we are using interval arithmetic with either the machine doubles or then with the extended multi-precision numbers as provided by the GMP library. With double-double and multiple-double arithmetic, one extends also the precision, but one exploits the hardware double arithmetic, which is not the case with the GMP libraries, which is software-driven. Okay, thank you for your attention.